Hello, this is Paul from First Tech. In this video, let's prove Theorem 3.2.4, which is a Cauchy-Schwarz Inequality. Okay, and the Cauchy-Schwarz Inequality is the foundation of the angle that we will define in n space. Okay, imagine this is a fundamental theorem. And the inequality is like this. Okay, in n space, the dot product can be controlled by the product of the norm, the distance. Okay, is this the super symbol? In another way, we can see in this. Okay, if we expand, see the dot product defined by the sum of products, right? And then the norm. This is the norm for u. This is the norm for v. Okay, the distance. Okay. Let's prove. To prove Cauchy-Schwarz, all we need is this one. Let's define. We need this important result, okay, which is up here is the norm of v squared times u. You will say this is strange, really. Okay, and then minus u dot v times v, the square of the norm. Okay, and see, this inside should be a vector, right? So this is a scalar multiplication. This is also a scalar multiplication of a vector. To subtraction, we get a vector, yeah, and space, and then the norm, and then square. And this should be equals, okay, the norm of v squared times and u squared times v squared, then minus u dot v squared, parentheses. Okay, can you see if this is true? Of course, so far we don't know. Okay, we will verify this equation. If this is true, and we definitely know this should be greater than or equal 0, right? Because that's the norm of the distance square. And this first term is greater than 0, and the second term, see, should be greater than or equal to 0. So therefore, the second term should be less than the first, and then take a square root, which is, if this is true, and we easy to see. The second term should be greater than 0, which means this square times v squared minus u dot v squared should be greater than or equal to 0, right? And then you work on. It's easy to get the result. So what do we have? We will have u dot v squared should be less than or equal to this term. And then take a square root, or the positive number, take square root. So we get, of course, don't miss the absolute value. And this should be less than or equal. Take a square root, which is this one times v. Yeah, because the norm is already non-negative. So this one should be true, right? So this is the Cauchy-Schwarz. Now the question is, how to do calculation? So can we find the square of the norm of this equal to this term? Why? We say the first equation. Okay, see, that's Just do calculation now. It's super easy. What is v squared u minus u dot v, and then we should times v, and then the norm square. So see, and this expression is the one at the first, okay, on the left. And you see here. Okay, so now we do calculation. So we need to find the result should be the square of the and this one times this term. If we find it, then we finish the proof. Is this true? Yeah, all we need is just expand, use this result. Okay, remember if w is a vector, whatever, and this square, how to do calculation? We use w dot w at the self, right? Just use this small result. So w is the bigger term. So we need to do this calculation. Square times u minus, oops. Okay, so this is w, and then dot times w at the self. So, oops, let me put. So minus u dot v times v. Okay, so and then distribute it. And then distribute it. We know the distributive property works, right, for the dot product. And every distributor we should have 4 terms. So let's do the first term. So the first which you look at this term, and this term is v raised to the 4th power, and then u dot u. What is u dot u? U dot u is just u, the norm square, right? So this is u dot u, keep in mind. So u dot u equals the norm of u and then square. Okay, so we have the first term. And then look at the second term. Look at the outer term. Okay, so this term and this term. What do we get? We will get u dot v, u dot v. So we have a u dot v raised to the 2nd power, and then the norm, right? So this is negative. So minus v square, and then u dot v square. Okay, so this term. And then I look at which term we use. We look at the middle term. Okay, the middle term, the inner term. Let me simply say this term with this term. What do we get? We get a negative again. Okay, so let me still put here. So negative what? Negative the normal square is still there, and the u dot v and v dot u. V dot u equals u dot v. So therefore we still have u dot v squared, which is the same as this term. See, and then u dot v squared. We already used the symmetry property or the commutative. And then we have the last term. Okay. The last term, we say this term, and we'll look at this term. These 2 terms, u dot v, so u dot v is to the 2nd square, and then v dot v is the square of the norm of v. Okay. So therefore, one more term. Let me put it here. The last term is positive. Negative, negative makes positive. So plus I can switch the order. Which is v dot v is the normal square, right? So v square, and then u dot v also square. Okay, so let's cancel. This term and this term are the same. Okay, so disappear. So we only have 2 terms left. Let me copy, and the 2 terms left. See, so v raised to the first power times u, the norm of u raised to the second power minus the norm of v squared times u dot v squared. Okay, so we factored out the common. Okay, this is the common. The common term we factored out, which is a v norm of v squared, and then what do we left? Okay, we left the u switch the order. Okay, so u squared times v, the norm of v squared. Okay, that's the first power. So take out the 2, we have 2 left. Then minus u dot v squared. Okay, put is these 2. See, definitely this is the verification. So v square and this minus this you can compare to the beginning. The norm of v square times this. Okay, so this term greater than 0, therefore, and the Cauchy-Schwarz is true. Okay, so that's true. That's the proof. Thank you.